Hello everybody, nice to see you here today. I'm going to present my thesis work called the SST paradigm as a tool for supporting software maintenance. Today, first I'm going to discuss the research area, then I will move to the solution. After that, I will explain the design and implementation. And finally, I will discuss the applications of the proposed solution. First of all, the research area. Why are we doing the project? Our research area is the software maintenance. Software maintenance is a very broad and important field. It ensures long-term system reliability, stability, security, safety. Different estimates show that 40 to 90% of total software costs occur during the maintenance. So it's a very broad field with many challenges. We are not able to support each and every challenge, so we are focusing mostly on big systems and big problems. So our main focus is the large systems with outdated legacy code base, with poor or missing documentation, complex fragile code, and systems where we have many original developers missing. So we have this problem that a lot of information is missing. We need to recover some knowledge. And to do this, to recover this essential information to continue doing the maintenance and try to fix this system, people usually rely on reverse engineering and software analysis tools. Those tools are essential to help engineers to analyze, understand, and modify complex legacy systems with limited documentation and outdated code. So those tools helps us to do the maintenance. They help us to do the maintenance process. So they focus on very diverse set of maintenance areas, including performance improvement, security enhancement, bug fixing, documentation, and many other areas. So we have a lot of tools and a lot of opportunities to help us to do the maintenance process. And once we are using only one tool, everything works good. Most of them are pretty much user-friendly, so we have a good user interface. We are able to work with this tool. But what happens if we need to use more than one tool? Here is where we face the actual problems. So I was able to identify 5 main problems once we starting combining those reverse engineering and software analysis tools. So the first problem is the incompatible formats. Each tool gives you information in a different format with different interface. So it's tried to work with more than one tool. Another problem is the large amount of data. Working on large systems, we have this problem of the large amount of data that is very hard to understand for a developer. That's why we need some external helper. Another problem is lack of unified understanding. So we struggling to combine and unify the information from those reverse engineering tools. It is hard to do it in your head, so you need to somehow unify it. Another problem is difficulties in traceability and analysis. It is very important to know where the data comes from and to know how you can analyze it to make some insights and maintenance decisions. And the final problem is the data consistency and duplication. Working with those legacy systems, we can often face those consistency issues that would add some noise and that would affect our maintenance decisions. So all this brings us to the conclusion that data needs to be integrated. But the question is how? that is exactly what I'm going to explain in the next section. So the next section is our solution. First, imagine having a large legacy systems with the problems I described before. You have outdated code, some performance issues, security issues. So you have some troubles while doing the maintenance. So you start using those reverse engineering tools. For example, you take one tool that gives you performance measures, another tool gives you code structure, the third one gives you security data, and the fourth gives you issue tracking information. So you try to combine it in one place, you try to unify this information, but the question is how to do this. There are many approaches that helps you to do the data unification and integration. So probably the most straightforward one is the data-driven integration. The idea is pretty much simple. You take the data and put it into some data storage. You write some SQL query or Python script that helps you integrate the data. But the problem with this approach that it is very rigid and domain specific. So the problem is that it is not scalable and it won't probably work for another scenario. So it is not universal at all. And the other approach that you can use is the machine learning and AI based integration, very popular those days. So it is quite useful in terms of uh, the usability. It is quite easy to use some AI technology that will do the work for you. But the problem with those solutions that it has lack of control and transparency. The problem with AI-based integration is that it works like a black box. So you don't know what is going on inside. So you cannot rely on the process while doing the maintenance. And the third approach that we can use is knowledge-driven integration, probably the most powerful in terms of reliability and transparency. But this approach usually requires building some kind of ontology, and it requires some expert input, and it might be quite complex to build. So building an ontology requires some time and some effort. So it might not work for the maintenance scenario. But on the other hand, we have a single source of truth approach. This approach is based on three main properties. So the first one is it tells us that we have to support multiple data sources. The second is that we have to build a single data storage and we have to aggregate all the information in a single place. And the third property, the most important one, that we have to ensure data reliability and transparency. This is what the single source of truth approach paradigm is about. But why is it a good solution for our software maintenance case? So remember those 5 challenges that I described before. So first, we have incompatible formats. The SST can handle it. We can handle diverse formats and data structures in the SST by the definition. The second challenge is large amount of data. The SST provides you a data storage that should be able to consume this large amount of data and store it. The third challenge is lack of unified understanding. And that's exactly what single data storage about. You can unify all the data in one single place, and that would be very helpful. The fourth challenge is difficulties in traceability and analysis. Here is where we have a single data storage that can help us in the analysis. So we can perform some analysis on top of our data because the data is in one place. So we don't need to go and gather this data. And we have traceability that is ensured by the data reliability and transparency property. And final problem that we're addressing is data consistency and duplication. This is exactly what the definition of data reliability and transparency about. So it helps us to focus on these data issues. But the SST is only a paradigm. It's only a concept, a high-level guideline, how we should implement the system. So it is not something real yet. That's the main goal of my research, to implement the SST in a software maintenance context. So the SST is a guideline, and I have to make it real in the software maintenance concept. Here is what are the major goals. So first, we have to support diverse set of maintenance data providers. We have to create a single data storage, and we have to ensure reliability and transparency of the data integration. But it is very easy to say. There were a lot of challenges and problems during those 2 years of development. So here are the main challenges that we were able to overcome during this work. So first challenge is how to support heterogeneous data sources, how to gather this data, how to handle it. The second challenge is what data structure to choose. The next challenge is how to define data abstractions and schemas. We need to make sure that we understand the data schema. And the final challenge is how to integrate heterogeneous data while ensuring consistency. So here is a list of challenges, and I will explain you the design and implementation of each of them in the next chapter. So first of all, how to support heterogeneous data sources. And our solution here is the concept of probes. So probes are data connectors between maintenance tools and the SST system. So basically, everybody can implement these data connectors following our predefined standard. So you can take any data, you can implement this probe, and you can use our SST and all its benefits. Pretty useful, I believe. So here is what benefits we get from this concept. First of all, it is a single standard for diverse tools and formats. So any tool and any format can be integrated into SST by implementing this probe adapter. The second benefit is it enables independent data extractions. So you don't care about the tool itself. The tool can work in an asynchronous way. And after it's done, you can just take the output, the result, and put it into SST. And finally, it makes the system extensible. Basically, you can plug in as many tools as you need, and the system should work fine. So this is the probes concept. The next challenge was what data structure to choose. And the answer here is the graph data storage. So which rely on the graph data storage as the central storage of the SST system. And here is why. First, it naturally handles relationships, supporting our heterogeneous environment, because we don't have the rigid understanding of the data. We rely on the graph to naturally handle all the relationships and all the dependencies in our heterogeneous data. The second benefit is that graph data storage is quite flexible and scalable. You can add as many data as you want, simply adding relations between the nodes. And final benefits is that it enables efficient and insightful queries over the connected data. One of the challenges in the maintenance is to understand the dependencies between the data. So you need to get those powerful queries on top of the graph data structure to understand that all the dependencies chains in the maintenance data. So the next challenge was how to define the data abstractions and schemas. And here is what we have done. So we invented a type system that basically is a data schema for all nodes and edges. So this type schema is required to be provided by each probe. So probe tells you what kind of data it will provide. So for example, you can think about the type system as classes, as a UML class diagram, for example, or SQL schema. So this defines you what kind of data we are expecting, and this is why it is beneficial. So first of all, the type system allows probes compatibility to be ensured at the type level rather than the data level. So in other words, before the pushing the actual data, we are able to tell if the data is compatible together. So it's very useful so we can understand what kind of data we are working with during our maintenance process. So another benefits of this data schema is that it helps us to support system consistency, implementing data validations and constraints. So we having this schema, we can expect some kind of data types to be provided, and we can implement those validations and constraint to prevent some unexpected data. So the final challenge in the design and implementation was how to integrate multiple graphs. So imagine each probe provide you some kind of graph and you need to unify them. So how to do this? Here is where we rely on the graph merge algorithm. Here is how it works. Imagine you have two graphs and they provide you the nodes of the same type. Basically, they provide you equivalent data. And in the result graph, you will simply merge the equivalent data. This is how the graph merge concept works. So this allows you to simply integrate and unify multiple graphs. And here is why it's beneficial. So first of all, it is a reliable way to unify data and support incremental updates. So you can, so first of all, it is basically deterministic. So you can push the data, and this allows you to do it in incremental way, to do it step by step using this graph merge algorithm. The second property is that it is idempotent. In other words, you can push as many times as you want, and you will end up having the same graph representation because all the duplication will be absorbed during this graph merge. So no matter how many times you push the same information, the result would be consistent and accurate. And the final properties that it is associative and commutative. This gives you very important scenarios where you can push the data no matter what order, and you would end up having the same consistent graph representation. So you don't have to care about what data should I push first. You can push the code data, the performance, etc., no matter what order, it would end up having the same graph representation. So in other words, this very predictable, transparent, and consistent way to integrate the data. So this was the main design and implementation challenges that we had to solve. And now I'm going to explain how can we apply the developed system. So here is what we are doing to evaluate the proposed system. First, we selected an open source Spring Pantelic application This is a demo project implemented by the developers of the Spring framework. Those developers show how the Spring framework can be used. So this is a very popular open source application that is used for demo purposes mostly. That's why we selected it, because we need to have some system to evaluate our SST. So we didn't want to go immediately to some complex legacy system. It won't support the evaluation process. So we need to have something reliable and sustainable to work with to evaluate our technical implementation. And another benefit of this use case is that it has a very common technology stack that used in many other applications that can give them some inspiration how the SST could work on this technology stack. Oh, I think I will be on time. So our Spring Pet Clinic application was used in this way. So first we take those reverse engineering and analysis tools. We implement probes, we push the data, and we get this unified data structure. And then we can do some analysis and graph queries on top of this data. So here is how the data looks like, and here is what we can do with it. So first, basically, we can identify the code structure of the data. Then we can spot some performance issues because our performance data is merged on top of the code structure. And then we can trace slowness distribution over the system. You know the execution chain of each method, and you know the slowness, so you can trace this slowness distribution over the execution chain of methods. And finally, you can spot the developers. You can query the relations between developers and slow methods, and this will get you some insights who can help you to solve the slowness. So it's not the only use case that we have for the SST. Another scenario was a microservices use case. It shows us that the SST can be used in other scenarios. And another important scenario was a large scale data. We were able to handle a large Java code base, Java code structure of a large Java applications that had like 3,000 of methods and classes. That gives us insights about the performance compatibilities, and we didn't face any significant performance issues during this use case. So we assume that we are able to handle large system and large data. So here is a list of potential use cases that we can use from our understanding. So we can apply the SST to solve the performance optimization, bug localization and fixing, security enhancement, team collaboration and code on ownership, API and architecture exploration, and software documentation and onboarding. So we can basically imagine as long as we want, but the main problem here that SST is very good implemented from technical point of view, but we still need to have some maintenance-driven environment. So we need to find a real system with real problems to use it with the SST, because we need to connect with real people, with real processes, and see how we can support their day-to-day work. So in conclusion, here is what we were able to do with the SST. So we were able to support diverse set of maintenance data providers using the concept of probes. We were able to create single data storage using a graph data structure. We were able to ensure reliability and transparency of the data integration by having the concept of type system and graph merge algorithm. But in future, we have a lot of work to be done to make the system much better. So in future, we expect to improve the graph-based processing and performance. So far, the SST is implemented probably at the MVP stage. So everything is working. We're able to support the maintenance scenarios, but probably we need some more advanced features in graph processing, performance, and other areas. So we need to make some work to improve it. And another useful property is to support advanced analysis techniques. Having this unified graph representation gives us a very large area of the analysis. So we can apply some machine learning on top, some analysis, some graph, advanced graph queries on top of our system. That would be probably very useful for maintenance. And another scenario is we might explore how the SST can address data completeness. So we want, having this graph representation, we can see if we have enough information to cover all the data, or maybe we have something missing. We can see if there are some holes in the data, maybe some inconsistencies, so we can make this analysis. And final, maybe a very long-term goal is to create a marketplace of those maintenance data providers, a marketplace of probes, to make the SST a community-driven tool. So once we have enough tools to work with SST, we can put it to the community and just rely on the community decisions, but not make implementation of the probes ourselves. So this is all I wanted to discuss for today. Looking for your questions.
Okay.